The Northwest Highlands of Scotland probably has the best scenery and geology in the world. You can find the oldest rocks in the British Isles, the first evidence of life, ancient landscapes carved out by Precambrian rivers, and beautifully exposed lower Paleozoic clastic and carbonate sediments. These all form part of a major fold and thrust belt on which the metamorphosed Moyne schists were emplaced. However, geologist Roderick Impey Murchison saw this as a conformable succession. It is worth asking the question, why did Victorian geologists so completely miss the evidence that is so obvious to geologists today? The answer lies in the state of geological science at the time, geopolitics, and social climbing. Resolution of the Moyne thrust controversy was the turning point in the history of geology that gave us the foundations of geological science as we now know it. Well, thank you very much for inviting me to give my presentation on the Northwest Highlands controversy, geology, geologists and social climbing in Victorian times. This takes place in my opinion, the most beautiful place on the planet. And this story concerns the geological history of one of the most interesting parts of the geology of the British Isles. And it also spawned a controversy during Victorian times. So it's got a very important story to tell for the history of geology as well. Now, this is the geographical area where the action takes place. The Moyne thrust outcrops from Skye in the south, all the way up the northwest coast of Scotland to Durness in the far north. The picture in the background is a picture of the southern end of Loch Erriboll, roughly here. And these areas highlighted in blue are really the key grounds in which this controversy was played out. We have an area in the south around the mountain of Sleoch and Loch Maree. We have a central area around Inchnadanf and Assynt. And we have this area in the north around Durness and Loch Erriboll. The patches between, we see the Moyne thrust exposed, but the exposure is a bit poorer and you don't really see the key features. So the areas, those areas highlighted are really the key areas. And the history, the geological history that I'm going to be discussing starts right at the oldest rocks in the British Isles, the Lewisian, which go back to 3,200 million years, right through to the Moyne thrust that took place at about 425 million years. So this story really covers pretty much half the history of the planet. So if we start at the bottom of the pile, we're down here looking at the oldest rocks in the British Isles, the Lewisian gneiss. Now, if you put the North Atlantic back together, these form a continuous basement block that you also find in South Greenland and also Eastern Canada. So the story the geological story sort of continues. You'll find parts of it on the other side of the Atlantic there. Now, this is probably the second most complicated outcrop in the British Isles. The oldest part of the Lewisian is these very grey gneisses. These are very highly metamorphosed rocks. So these grey elements here probably represent the oldest part of the Lewisian complex. Then you have these black rocks, which were originally basaltic dikes that were intruded into the Lewisian complex, and that took place at about 2,200 million years ago. Then you have these very coarse-grained vein rocks, which are called pegmatites because they have very large crystals of quartz feldspar and mica in them. And those were intruded in, these are about 1,800 million years old, and these are known as the Laxfordian pegmatites. So there's a very complex history involved in simply the deposition, metamorphism and deformation of the Lewisian, and that covers about half the planet's history. If we skip up an unconformity, the pink bits in this column represent unconformities, so these are gaps in the geological record. We then see the first sediments in the British Isles, the first non-metamorphosed sediments, I should say. And this is the Store group. These are some red beds, they're sandstones, conglomerates and shales, and these are about 1200 million years old. And these were deposited in a series of isolated rift basins. And you see, if you map the unconformity, you'll see that it's being deposited over a very, very rugged land surface with these very steep valleys in it, and these conglomerates are infilling these steep valleys within the former landscape. And the Store group also contains the very first evidence of life, because further up in the succession, above the basal conglomerates, you see mudstones, which are mainly lacustrine in origin. So these were deposited in lakes. And some of the lake margin deposits contain these carbonate layers, which appear to be domical-like structures. And there's a much larger structure here. This is a pile of Lewisian conglomerate, and it's been encrusted by this red mudstone, and you can see that the laminations within it form this domical structure. And there's some debate about what these structures are. They could be stromatolites, which is the binding of sediment by microbial films, or it could be just microbially mediated deposition of carbonates. But whatever their origin, it's telling you that there was life on the planet at this time, some 1200 million years ago. Now, if we hop across another unconformity, we now see another very thick sandstone sequence, the Torridonian. This is much of these very large mountains immediately to the west of the Moyne Thrust are made up of these Torridonian sandstones. Again, these are red beds, and these were deposited as very large alluvial fans, because across in Canada, we had a fairly major mountain belt. So these alluvial fans and river deposits were draining a mountain belt, probably the size of the Himalayas today. Now we don't really see much evidence of the tectonism. This is called the Grenville orogeny. We don't see much of the tectonism, evidence for the tectonism in Scotland. Most of that story is over the Atlantic in eastern Canada. But it's these mountains that were being eroded to form this enormously thick pile of sandstones. The map here shows the outcrop, but the diagram has actually been stretched to take account of the displacement on the Moyne Thrust and on the Outer Isles Thrust, which is a connected thrust belt to the Moyne Thrust. Okay, then we have, above the Torridonian, we have yet another unconformity. And on top of that, we have got a series of sedimentary rocks ranging in age from Cambrian to Ordovician. And we have, this is a very consistent stratigraphy that you see throughout the Moyne Thrust, and it really assists structural geologists to try to understand the actual structure within the Moyne Thrust zone, because these are very readily mappable units. They're highly distinctive. At the base, we have basal quartzite, which is a very pure quartz sandstone that was deposited in a high energy marine environment. And that passes up into a so-called pipe rock member, which has these structures in it. You can see the laminations picked out in red, but there's also these vertical white streaks going through them. And those were burrows, they're burrows. So creatures were actually living in this mobile substrate, stabilizing the sediment so they could live there. go further up the succession, you see there's a sort of very fine-grained silty or shaly member, so-called fucoid beds. This is a siltstone with these wave structures in, and it also contains trilobite traces. And the actual name, the fucoid beds, is a misnomer because the early geologists who worked there saw these trilobite beds and thought that they were traces of seaweed, hence the name fucoids. And then above that, we go into another very pure quartz sandstone called the Saltarella grit. Saltarella is a tiny little gastropod that lives there, or is preserved there, shall we say. Then further up the succession, we go into a largely carbonate interval called the Durness limestone, and this has been subdivided into various formations. And this was deposited on a fairly shallow tropical sea. We have oolitic intervals within it, so part of the sea was very high energy above wave base, sediment particles being washed around in a high energy environment. Also, we have these very large stromatolites. That domical structure is about 10 or 15 meters across, and this is built by the accretion, trapping and accretion of sediment in by algal mats. And it's a bit clearer in this part of the succession that we that these are definitely stromatolites. Now, we have to step back a bit in time because the next rock unit above these Cambrian Ordovician sediments is the Moyne Thrust. And on top of the Moyne Thrust, we have the Moyne metamorphic sediments deposited on top of them. And these are between about 870 to 1,000 million years old. And they are partly equivalent to the Applecross group, which is part of the Torridonian. And there are also, I mentioned that the outcrop of the Lewisian was the second most complicated outcrop in Britain. The first most complicated outcrop in Britain is where you see the Moyne rocks unconformable on top of the Lewisian. So you've got the Lewisian deformation to think about, and you've also got the deformation and metamorphism of the Moyne rocks to think about on top of that. So this is the rocks. These Moyne rocks are the ones that were carried by the thrusting and placed on top of the Cambrian Ordovician sediments, the Torridonian sandstone and the Lewisian basement. And you can see evidence of this or throughout the outcrop of the Moyne Thrust. This is a large-scale view looking up Glen Cool. This is just to the north of Assynt. And this is roughly the cross-section published by the Geological Survey in 2007 that shows the east side of Loch Glen Cool. And you can see the Lewisian in red. You can see the Cambrian quartzites in grey. That's this outcrop here. And then above them, you have all these minor thrust structures, which is this structure here. And on top of that, you've got another thrust where the Lewisian, you get a repeat of the Lewisian on top of the sandstones. And that's part of the Moyne Thrust complex. At a slightly smaller scale, this is just to the south of Assynt. This is the Strancruby Cliffs, just to the south of the Assynt Inchinamp Hotel. The picture you can see in the background is probably that part of the cross section. So you've got a little culmination there, which is probably that. And then on top of that, you've got these parts of the Durness limestone that are stacked up against each other like dominoes that have not quite fallen over. And so at the base of the hill, you've got conformable quartzites and pipe rocks. And then you've got a thrust coming through here, and all of that's being carried up to the west in this case. And you can see the evidence of thrusting at a really small scale as well. These are a couple of road sections by Loch Eribol and further south at Elphin, which again is near Inch-na-Damh. And the red lines I've put on are these minor thrusts. And you can see these are affecting the Durness limestone, and the blue lines I've put on are bedding in the limestone. So you can see how that limestone bed and the limestone beds above it have been carried up on this red thrust, and again there and here, and so you've got several thrusts. That thrust is cut an older thrust, and you've got a slice of displaced limestone here, and then you've got the limestone beds on top of that thrust there. So it's really quite a complex structure once you really get into it. And having seen some of Rob Butler's videos on YouTube, the scale of thrusting can really go down to almost hand specimen scale. Now, very conveniently, the Moyne thrust has been intruded by a number of igneous rocks. So you've got igneous rocks that are cut by the thrusting, which clearly predate the thrusting. And you've also got some other igneous rocks that are either being deformed during emplacement or post-date emplacement. And these can be dated. And so this gives you a window between about 430 million years and 426 million years. That's the oldest post-thrust rock and the youngest pre-thrust rock. So the time difference gives you a window in which the thrusting happens. So we're looking at a time difference of about 430 to 426 million years, which puts us pretty much bang on the Silurian-Devonian boundary. Okay, so that's the end of the first half of the talk, and that expresses the sort of modern view of the geology. Now, it wasn't always like that. When people were beginning to work on this area back in the early and middle Victorian times, two very separate views developed. We have James Nicoll, who was the chair of natural history at Aberdeen University in 1853, and he did a lot of work on the relationships between the Moyne rocks and the older rocks. And this is the result of some of his field work he published as a series of cross sections through the Moyne thrust. And he noticed several things. First of all, he noticed that there was sometimes evidence of an igneous intrusion and or crushing at the base of the Moyne contact. He also pointed out that there was stratigraphic anomalies. So as you measure sections at various points along the outcrop of the Moyne thrust and note down the stratigraphy, you get different answers. So he was saying the stratigraphy is not constant. And he also pointed out that faulting was often associated with the Moyne contact. Now, on this cross section, he shows some faults, but he shows vertical faults, not horizontal faults that we now know are present. So yes, he sort of got it right, but he didn't get the orientation of the faulting. Now, in opposition to this, we have Roderick Impey Murchison's hypothesis. And what he said was the Moyne are sediments of Silurian age. They're constrained by datable fossils and are overlain by the old red sandstone. Now, he had some fossils brought to him, collected from the Durness limestone on the north coast of Scotland, and he identified those as lower Silurian fossils. So, and then he said, okay, if you walk along the north coast of Scotland all the way to the east, you keep going through these Moyne rocks, and then you find you're in the Devonian old red sandstone. So logically, he said the Moyne rocks are a conformable succession that pass up from the Cambrian and are unconformably overlain by the old red sandstone of Devonian age. And he also said the succession resembles that of the Welsh borders. As I'll explain, he was very familiar with the geology of the Welsh borderlands, where you have a quartzite, Stiperstone's quartzite, overlain by Silurian shales, which themselves are overlain by the old red sandstone. So he said the Cambrian to Silurian succession is conformable. But to make the stratigraphy work, he had to put two quartzites in the succession. There was the lower quartzite, which is what we recognize as the basal Cambrian quartzite. And he also had an upper quartz rock, which today we would also recognize as a lower basal Cambrian quartzite. And he says, yes, there may be local minor faulting, but there's no major displacement. Okay, so I did my undergraduate degree at Leeds, and it was a really strongly structural department at the time, and we were sort of indoctrinated or brainwashed, if you like, into structural geology, and there was a big group actually actively researching the geology of the Moyne thrust zone at the time, looking into the thrusting and doing all sorts of mapping. So the way we were sort of, this controversy was expressed to us was Nicol was the good guy who got the right answer, and he was oppressed by Murchison, who was the bad guy, and his false views prevailed because of his social and political connections in Victorian society. And this view persists to this day. This is a quote from a paper published as recently as 2019. It may be said with certainty that Geekie and Murchison made a monumental error in misreading of the rocks of the Northwest Highlands. Now, as you'll see later on in the talk, I won't be defending Geekie, but I think apart from that, that is a quotation is made with 2020 hindsight. Now, the sort of time frame over which this controversy happened, geologists began working on the Northwest Highlands in the sort of 1830s, people like McCulloch, and then Nicol from Aberdeen and Murchison and Geekie started paying attention to it during the 1850s. The controversy in favour of Murchison really became established in the 1860s. And then the controversy sort of carried on until it was resolved in 1884 by Peachhorn and Lapworth. So the controversy actually lasted about 35 years. So that's the sort of time frame in which it took place. This, again, just go back to the Rob Butler's map, is the geographical space in which it happened. The key areas are Inch, Nadamp and Asint in the central part of the outcrop. It was finally resolved by mapping in Loch Erribol, and there was also some interesting structures and work done on the Sleoch Loch Marie area. I think it's also worth pointing out that this was a time of immense popularity of science. Victorians couldn't get enough science, and all the meetings, the geological meetings where this was discussed at Aberdeen and Edinburgh and London, these would be covered in the press. So there'd be, I mean, Twitter's got nothing on it. You would expect most educated professional Victorians to have an opinion on this. Okay, so to introduce the main protagonists, starting with Murchison here. This is a picture, Rent Day in the Wilderness, commissioned by Murchison, and the artist is Edwin Landseer, and that really is Murchison. He modelled for Landseer, and what he's doing here is portraying his great-granduncle, Donald Murchison, who was the factor for the estate belonging to the Earl of Seaforth in Wester Ross. He managed it while the Earl of Seaforth was away, and this is him collecting rent off the tenants, supposedly. Unfortunately, the Earl of Seaforth lost back the wrong side in the 1715 Jacobite rebellion, so he lost it all after that. But Murchison came from a wealthy family. He was born in 1792. He had a fairly conventional upbringing. He purchased a commission in the army and served under Wellington in the Peninsular War, seeing action against Napoleon in 1808. But after that, his military career sort of fizzled out somewhat. And he ended up in a depot in Ipswich in 1815. And when all your mates are preparing for the big battle in 1815, and you're in a depot in Ipswich, he kind of took the hint that his military career was over. So he left the army, married a wealthy heiress, Charlotte Huguenin, who encouraged his interest in science. And he got interested by attending lectures by Sir Humphrey Davy in London. And he got interested in geology. Now, at this time, the stratigraphic column down to the Devonian was pretty much sorted out, pretty well understood. The big controversy and the big problem in the geology was these so-called transition rocks. These are what we now know as the lower Paleozoic rocks, particularly of Wales. And these, they're not very fossiliferous, they're a bit fine-grained and boring, and they're very highly deformed, and they were really poorly understood. So this was the big problem of the time. And Murchison and a geologist from Oxford, Adam Sedgwick, decided to try and sort these things out. So Murchison started from the top, working down. This is the current outcrop in Wales, or currently understood outcrop in Wales of the Lower Paleozoic. The dark ornament is the modern Cambrian. The grey is what we now call the Ordovician. And the white within this dotted line is the Silurian. So Murchison was working from the top down, defining his Silurian rocks. Adam Sedgwick was working from the bottom up, defining his Cambrian. And of course, each were desperate to claim as much of the succession for their own as possible. So there's this sort of demilitarized zone between the two workers. And this caused the first sort of major controversy in Victorian geology, and it wasn't totally sorted out in either of their lifetime. But that's really what got Murchison interested in geology, and he really carried through this interest in the Silurian right through to his work in the northwest Scotland. Okay. Murchison, being a wealthy, from a wealthy family, he was able to undertake these grand tours of Europe, as many people of his social class did at the time. And I think it's worth asking the question why he knew about the structure of the Alps. Why was that not transferred to his understanding of the Northwest Highlands? Because essentially the same thing's going on. We've got a collisional or orogenic belt in both cases. And at the time, European geologists were mapping these very large, what they call naps in the Alps. This is a compilation from Heim, a Swiss geologist, in 1878, but it contains work of much older geologists. So the nap is an enormous recumbent fold with a root zone that's been squeezed up and pushed over with probably several tens or even hundreds of kilometers of displacement on it. So this type of structure was certainly known at the time that Murchison was working on the Northwest Highlands. And also similar structures were being mapped by American geologists in the Appalachians at the time. So it's not as if this concept wasn't understood. And Murchison as a result of one of his grand tours through the Alps, published a paper in 1849 on the geological structure of the Alps, Apennines and Carpathians. And in the paper, he shows structures, he draws cross sections, and he clearly recognizes structures of this nature. So he can't be unaware of it. But the focus of this paper is entirely stratigraphic. He's only interested in the sediments. He doesn't really pay attention to the structure. And in his 1858 paper, he explicitly states that the Northwest Highland is or he was looking at the Northwest Highland as a stratigraphic analogue to the Welsh borders, where you have a very similar succession. So I think the reason this all bypassed him was he's entirely focused on the stratigraphy and establishing his Silurian system. Okay, now we need to introduce Archibald Geikie. Geikie was one of the sort of superstars of Victorian science. He was a very capable geologist. He had an absolutely stellar career, and he also did a huge amount of work in popularizing geology. And probably the sort of modern equivalent of Archibald Geikie would be somebody like Brian Cox or Stephen Hawking. He was a prodigy. He published on geology in his teens. And at a young age, he was introduced to Edinburgh Scientific Society by Hugh Miller. He's the guy who found the fossil fish in the Old Red Sandstone in Scotland. And at this time, Murchison was director of the Scottish Geological Survey, and he employed Geikie as a young survey geologist in 1855. And he pitched him straight into mapping the southern uplands of Scotland. Now, I'm going to come back to this interval because the geology of the southern uplands is actually very relevant to the discussion of the Northwest Highland controversy. And Murchison really took Geikie under his wing, and they went on in 1860, they went on a sort of grand tour of Scotland. And this is a watercolor sketch done by one of the guests at one of the hunting lodges they were staying at. And it's a bit unkind, isn't it, really? He's sort of portraying Geikie as a sort of sheepdog fetching rocks for his master. And I think it is really symptomatic of a fairly unequal relationship here. Geikie is the new hire of the Geological Survey. This is his boss, and his boss is taking him under his wing to show him around Scotland. Now, I think Murchison organised this 1860 tour with a very specific objective in mind, and that was to pass on not only his knowledge, but his model of stratigraphic conformity that he applied to the Northwest Highlands. So I think there was a subtext that may or may not have been explicit. Geikie was expected to take on board his boss's theory. And it must be said that I think the pressure increased on Geikie. In 1871, Geikie became the Professor of Geology at Edinburgh in a chair endowed by Murchison specifically for Geikie. And also, Murchison made Geikie the director of the Geological Survey in Scotland in 1869. So Geikie's sort of climbing the greasy pole was certainly assisted by Murchison. And in 1882, Geikie became Director General of the Geological Survey of Great Britain. Okay, so this is the outcome of Murchison and Geikie's 1860 tour. This is the map they published in 1861. And this shows quite explicitly a conformable interpretation of the succession as a conformable sequence of rocks from the west coast through to the east coast. And that's this blue is the Durness limestone outcrop, which approximately marks the position where we now understand the Moyne thrust to be. Okay. Another important character in the controversy is Charles Lapworth, who ended up as prof at Birmingham University. So he's almost a local lad. In the 1860s, he was a teacher in Galashiels in the southern uplands. And it was the Murchison-Sedgwick dispute in these transition rocks that got him interested in geology. And it probably wasn't long before Lapworth realized that he was living in the perfect place to make a contribution. And he tried to look at the stratigraphy in detail, and he did classic work on the Dobbs Lynn exposure, which is in the Silurian shales and sandstones. Now, what he found, he collected the zone fossils for the time, the graptolites, and what he found was that the stratigraphy comes at you in very short conformable packages, and each of these packages is bounded by a fault. Now, this diagram is the modern explanation of the stratigraphy that Lapworth found. What he found was that these are these individual packets of stratigraphy bounded by faults, and the whole package gets older to the north. Now, this is the explanation is this is an old plate boundary. This is the Iapetus suture, where we had England subducting underneath Scotland. And as the English plate subducted underneath Scotland, sediment got scraped up and stacked up against the margin in what we now know as a accretionary prism. Now, this is important for the Northwest Highlands, because the Geological Survey of the Southern Uplands were following the conformable model. They were assuming that everything this is a conformable stratigraphy, one after the other, no breaks. But what happened, what you find if you apply that model, is that in some parts of the area, you get units which are just unfeasibly thick, enormously thick units of a particular age. And in other parts of the succession, in other parts of the area rather, you find unconformities with unfeasibly thick, unfeasibly large stratigraphic gaps, so huge stratigraphic gaps or unfeasibly thick sections in some places. So the reason I'm discussing this in some detail is that in the case of the Northwest Highlands and the Southern Uplands, Murchison and Geekie failed to recognise repetition of strata by faulting. They were using the conformable stratigraphic model to try to understand both areas. And the third thing is that in both cases, it was Charles Lapworth who basically sorted out the problem. Now, this actually, the survey was working in the Southern Uplands 1850s to 1860s, and it really severely came back to bite Geekie later in his career, and it basically had to be redone in the 1880s and 1890s. Okay, move into the 1870s now. This was an important decade. Not a lot of new geological work was done, but firstly, 1871, Murchison died. This is his tomb in West Brompton Cemetery in West London, lying for eternity in the shadow of the Chelsea football ground. Do not underestimate the role of death in the advancement of science. So from then on, Geekie was still supporting the conformable model on his own. But there was some new geologists started working on the area, and they were coming up with observations that were casting the conformable model into doubt. For example, Callaway published the first sketch of what we now know as a thrust, but there was no unified opposing hypothesis yet. But I think the two key game changers was the style of fieldwork at this point changed, and secondly, thin sections became routinely used in geological studies. Okay, starting off with the fieldwork, pre-1870s, it's very much sort of grand tour style of fieldwork. Geologists would go on their grand tours around Europe, and they'd sketch things from afar they might collect, or examine a few localities. And in the case of the Alps, it kind of works. You've got 2 to 3 kilometers vertical relief, and you can see what's going on, more or less. If you try to apply this to Scotland, you've got a bit of a problem. You've only got a few hundred meters vertical relief, and instead of 100% of exposure, you've got peat bog, you've got clouds, you've got rain, you've got midges, you've probably got all four. And this is the type of sort of published results of the geological studies. You have these very generalized cross sections drawn. They're not particularly well located geographically, and they're probably drawn up from sort of distant views. Now, from the 1870s, you started to get publication of modern topographic maps in this area. And by that, I mean maps with contour lines on. And this really sort of revolutionized the process of geological fieldwork. Geologists, first of all, could locate their observations precisely on modern maps. So if you've been invited to a conference in Aberdeen or Edinburgh or London, you could actually argue about a particular thing, and everybody knew exactly what you were arguing about, whereas previously, without this geographical location, who knows, you could be arguing about different things. Secondly, maps are a means of recording data. This is the modern geological map of that area. And also, geological maps are a 3D interpretation tool. So this is not just a means of recording data. You can use it as an interpretation tool, and you can begin to understand structures and surfaces in 3 dimensions. And I'll give you an example of that. For example, you might want to look at the form, what structure is the unconformity, these various unconformities I've been talking about. So if we start with the subcambrian unconformity, that's the one at the below the basal quartzite. This is a geological map of Slioch in the southern part of the area. So what you do, you first of all locate the boundary. So we're talking about the boundary here between the blue quartzites and the brown Torridonian. So you follow that round, mark on where it crosses contours. These are all color coded, and then join the dots. So that shows you you've got essentially a planar surface, but one that's dipping very uniformly to the southeast. And if you go 50 miles to the north in a cint, do the same exercise. In this case, it's grey against the reds, oranges, and yellows of the Torridonian. Mark off the heights, draw the contours, you basically get the same answer. So this unconformity is regionally very planar. It's been tilted to the southeast. The photograph in the background is taken from the point of the arrow, looking in the direction of the arrow, and there you've got the nice dip surfaces of the sandstones with the Moyne thrust kicking in round here. If you do the same exercise at the base of the Torridonian unconformity, that's the unconformity between the Torridonian sandstones and the Lewisian gneiss underneath it. This is Slioch. Same exercise, so you've got the boundary between the brown spotty rock, the brown rocks of the Torridonian, and the green and red of the unconformity. Mark the heights, you get a very different answer. You get a very rugged unconformity. And you can see here, again, photos taken from that point, looking at that little hill in the Lewisian there, with the layered Torridonian on top. So essentially what you've got here is a mountain underneath a mountain. So that's the sort of insight that the maps can give you into the geology. The other game changer was looking at rocks in thin section. Now, Murchison and Nicol were using the old layered versus crystalline rock classification. And this really dates back to the long discredited idea of the Neptunist versus Plutonist concept, where you had crystalline rocks like this granite from the internet and this salt from Kuwait. These are crystalline rocks, and it was assumed that these were precipitated from the primordial ocean. And the other sorts of rocks were layered rocks. And the Lewisians are layered rock, the Moyne rocks are a layered rock, and the basal quartzite here is a layered rock. So these are all the same general rock type under this classification. Now, the implications of this, when you start doing field work, for example, if you're measuring a succession up Knockan Cliff, going from quartzites at the bottom, nicely conformable section, all through the Durness limestone, there's the Moyne thrust at the top with the Moyne sitting on top. Now, these are all layered rocks. So if you're describing the rocks systematically, there's no alarm bells going off in your brain to say that there's something dramatic happening there. And this is the classification that Nicol and Murchison were using. And looking through the papers I have, I can't find any evidence that either Nicol or Murchison ever looked at a thin section in their lives. So thin sections were around. They're actually around since about 1815, but they were first looked at in the 1840s by Sorby, who looked at some Carboniferous sandstones. But really, this is the basis of a modern understanding of rock types. And the first thing we noticed that there was the role of structural deformation in formation of rock types. If we look at two sandstones from the succession, basal quartzite near Loch Assynt and Saltarella grit again near Loch Assynt, these are normal sandstones. They've been buried a hell of a lot more than most sandstones, but you can see the grains, outline of the grains. They've just been compacted, and you can see quartz cement between the grains there and some carbonate cement between there. So those are just normal sandstones. Now, if you look at the Durness limestone, which is just below the Moyne thrust, you begin to see evidence of fracturing and crushing. So there's some deformation going on there. But the real revelation was when people began to look at metamorphic rocks in thin section. And it became evident that it's not only heat that's involved in producing a metamorphic rock, but also pressure and structural deformation. And I can imagine that anybody in the sort of late 1880s and 70s and so, looking at that for the first time, you must have instantly realized that everything you knew a minute ago just had to be completely rethought. So the origins of layering in metamorphic rocks is very much not the same as sedimentary rocks. And Nicol himself actually pointed out that it was illogical to have metamorphic rocks sitting directly on top of unmetamorphosed sediments. Now, that is regarded today as a key piece of evidence. But why was it not taken on board at that time? And I think the answer is that it's the concept of the origin of metamorphic rocks, because at the time it was thought that metamorphism, such as you see in the Moyne, was caused by heating by igneous bodies, of which there are plenty in the Moyne. But we now know that this contact metamorphism only happens over a few tens of meters. It does not, you cannot explain regional metamorphism by that. So the explanation of why you had metamorphic rocks on top of unmetamorphosed sediments, it could be just where the heat ran out. Okay, so Geeky is still hanging on to his support of Murchison's conformable idea. Everybody knows that Murchison has set up the chair of Edinburgh University for his benefit, and everybody knows that he's sort of career progression through the survey has been sort of assisted by Murchison. So Geeky decides to put together a team of geologists to try and sort this out. And this is one of the times in the history of science when absolutely the right people were available to do the job, particularly Ben Peach, John Horne. A perfect match between sort of intuitive thinker and systematic data gathering. Ben Peach was the sort of person who'd go to bed with a problem and wake up with the answer. And that it wasn't just those two. There was a team of other geologists as well, so-called Bandit's Lair, as they titled themselves in this photograph, and also two geologists not pictured, Clough and Teal. Teal was the one who worked on the thin section, so he was back up in the lab. And I have this picture of sort of lunchtime in the Geological Survey canteen in Edinburgh. Nobody speaking, two groups at opposite ends of the canteen, because it cannot have escaped these guys' notice that the most likely outcome of their work was to discredit their boss. And I mean, it must be said that these guys weren't going to do the work with a totally blank sheet of paper. The survey had set up a team of petrographers to work on thin sections in the late 1870s. So these guys must have known about the petrographic work that was sort of undermining Geeky's conformable hypothesis. Okay, so we move over to resolution in 1884. This is when the Peach and Horne team and Lapworth's work really came to fruition. The Lapworth and Peach and Horne actually met in the field on the east side of Loch Eriboll. And it's really down to Lapworth's detailed mapping of the structures on the east side of Loch Eriboll that really clinched the argument. Peach and Horne at the time were mapping around Durness, which is just over the other side of that hill. The Moyne thrust's exposed there, but it's not particularly good quality exposure, and the structures aren't really that characteristic. So it's really east coast of Loch Eriboll that was the key area. Now, one of Murchison's predictions was that there was two quartzites in the succession, a lower quartzite and an upper quartzite. And Lapworth proved this in possibly the best way he possibly could. And really, if this story is true, there really ought to be a Lapworth walk on the east coast of Loch Eriboll. He took Peach and Horne out in the field with him, and he stood them on an outcrop of Murchison's lower quartzite, and he walked them round on exactly the same, keeping to the same bed until he got to Murchison's upper quartzite. Problem solved. So there's only one quartzite, and any repetition is by folding or thrusting. Lapworth made a direct comparison of the structures he was mapping in Loch Eriboll with the structures we've seen in the Alps. And he also followed up the thin section work and did a lot of subsequent research on deformation fabrics in rocks. So to conclude, we have these opposite views of Nicol and Murchison. Nicol presented a series of observations. They weren't really they didn't amount to a joined up theory. He certainly didn't recognize the large scale, low angle faulting with large displacement. And that really is the key to the problem. So I think it's difficult to argue that Nicol got it anywhere near right. Murchison presented a testable hypothesis. Murchison, I would argue, is doing science and came up with the best explanation given the state of geological knowledge at the time. But as we've seen, I think geological science needed a reboot before Murchison's hypothesis could be fully tested. Now, scientists today still revere Isaac Newton. They don't revile him for not knowing about theory of relativity or quantum mechanics. But that is the sort of reboot geological science needed before this controversy could be settled. So, thank you.